Okay, in previous class we discussed the concept of atomic structure and modules of atoms, Zeeman effect, Stark effect, black body of radiations, spectrum, line spectrum of hydrogen atoms, etc. In this module, we have to learn the concept of quantum numbers. Just we glance that Bohr's atomic model, the electron in an atom surrounding the nucleons at particular energy levels. These energy levels are called what? Orbits. Each orbit contains sub-energy levels, and these sub-energy levels have specific orientation and are called the orbitals. This atomic orbiter describes the regions of space in which there is a high probability of finding the electron. In a multi-electron atoms, means more than one electron atom, that is what? Multi-electron atoms. All the electrons are distributed to different main energy levels, sub-energy levels, and oriented in different directions. The particular electron in such atom is identified using 3 quantum numbers. The 4 quantum numbers introduced in order to distinguish the pairing of electrons. That is what? Spin quantum number. The numbers which identify the state of an electron specify the energy associated with it and its location around the nucleus are called quantum numbers. These numbers are used to designate and distinguish electron in an orbiter. There are 4 quantum numbers, namely the principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. The atomic orbitals can be completely described using a set of 3 quantum numbers, means principal, azimuthal, and magnetic quantum numbers. These quantum numbers partly describe an electron in a particular orbit. In order to completely specify an electron in an atom, a 4th quantum number is called spin quantum number has been introduced. The principal quantum number is denoted by the symbol is n and can have the value of whole number 1, 2, 3, 4 up to infinity. This principal quantum number specifies the main energy level, means orbit of an electron and the size of the orbit. If n is equal to 1, called first energy level, that is K shell, n is equal to 2, second energy level, that is M shell, n is equal to 3, that is third energy level, that is N shell. Just we have to change here. N is equal to 1, that is K shell. N is equal to 2, that is L shell. N is equal to 3, that is M shell. N is equal to 4, that is N shell. This quantum number is labeled as principal because the values of defining two quantum numbers are defined only after the defining value of N. All the orbits that have the same value of N are said to be in the same shell or level. For hydrogen atom with N is equal to 1, the electron is in its ground state. If the electron is in that N is equal to 2 orbital, it is in the excited state. The total number of orbitals for a given N value is equal to 2. The simple examples. What are the significance of these principal quantum numbers? The principal quantum number gives the energy of an electron. All orbits that have the same value of N must possess the same energy. The number of orbitals present in a particular energy level N is equal to the value of N square. What is the first energy level here? 1. N square is equal to 1. Energy level 2, N is equal to 2. That is N square is equal to 2 square. That is equal to 4. That is the third energy level. N is equal to 3. Has N square is equal to 9. Has 9 orbitals. The total number of electrons occupied in a particular energy level is equal to 2n square. If n is equal to 1, we can accommodate only 2 electrons. If n is equal to 2, we can accommodate 8 electrons. N is equal to 3, we accommodate 18 electrons. N is equal to 4, we accommodate 4 square. Here 2 into 4 square means 32 electrons. In that second energy level, N is equal to 2, maximum we can accommodate only 8 electrons. In N is equal to 3, maximum accommodate 18 electrons. In N is equal to 4, accommodate 32 electrons. What is the conclusions of this? The electrons are accommodated in any atomic orbital is maximum is 2n square. The next quantum number is azimuthal quantum number. Azimuthal quantum number, that is also called subsidiary quantum number or sub-energy level. This azimuthal quantum number is also called the angular momentum quantum number or secondary quantum number, that is denoted by the symbol is small n. This quantum number specifies the sub-energy level or sub-orbitals present in a particular energy level n. It also specifies the shape of an orbital. Thus, the secondary quantum number divides the shells into smaller groups of orbitals called subshells or sublevels. The azimuthal quantum number L can have the value 0 to n minus 1. because that n is equal to what? N minus n into n minus 1, not n minus 1. Here n is equal to 1, the L value is equal to 0, that is K shell does not contain any sub-energy levels. N is equal to 2, that is one value, that is L shell, 2 sub-energy levels denoted by 0 and 1. N is equal to 3, L is equal to 3 minus 1. What we are getting? 0, 1, 2. This means that M shells has 3 sub-energy levels denoted by 0, 1 and 2. Usually, a letter code is used to identify L to avoid confusions with N. Corresponds to the letters, that is S, P, D, F, Z, H. The subshells with n is equal to 1 and L is equal to 0 is the first subshell. With n is equal to 2 and L is equal to 1 is the 2 subshells. N is equal to 2 and L is equal to 1, that is 2s subshells. N is equal to 3 and L is equal to 2, that is what? 3 subshells. And n is equal to 3 and L is equal to 1, that is 3p subshells. Here n is equal to 3 and L is equal to 0. That is what? 3s subshells. The value of S also has the slight effect on the energy of subshells. The energy of these subshells increases with L. What are the significance of this azimuthal quantum numbers? This azimuthal quantum number, it explains the angular momentum of an electron. It is used to classify different quantum mechanical states on the basis of angular momentum. It gives shape of an orbital. The magnitude of L denotes the energy levels of the orbitals. The next quantum numbers, that is magnetic quantum numbers. The magnetic quantum number denoted by the symbols M and can have the values of plus L and minus. This quantum number arises because M affect the energy of the electron in an externally applied magnetic field. Thus, the magnetic quantum number specifies the orientation of orbitals in a space of a given energy and shape L. The quantum number divides the subshells into their degeneracy levels. The orbitals which have the same level but different orientation in space are called degenerate orbitals. The total degeneracy of the orbital is equal to M is equal to 2L plus 1. For L is equal to 0, M is equal to plus or minus L, that is also 0, M is equal to 1 only. This means that only one s orbitals, no degeneracy. In that L is equal to 1, M is equal to plus or minus L, that value is minus 1, 0 plus 1. M is equal to 2L plus 1, here 3. This means There are 3 p orbitals, means p orbital is triplet degeneracy. They are denoted by px, py, pz. For L is equal to 2, M is equal to plus or minus L, that is equal to minus 2, minus 1, 0, plus 1, plus 2. And M is equal to 2L plus 1, totally 5. This means there are 5d orbitals is pentadegenerate. They are denoted by dxy, dyz, dzx, dx square minus y square, and dz, and so on. From these magnetic quantum numbers, as the name suggests, tells you about behavior of action in magnetic field. It gives the most important significance, orientation of orbital angular momentum, gives the energy of different orientations. There are 3 quantum numbers describes the properties of the orbitals in an atom. Thus, we can use the same quantum numbers to describe the orbitals of an atom. An additional quantum number is needed to describe the property of the electron in many electron atoms. The additional quantum number is called what? Spin quantum number. Like each charge, spin is an intrinsic property of the electron, and electron spin becomes important when more than one electron is present in an orbit. Finally, spin quantum numbers. We just imagine this is orbital. Any orbital accommodate only 2 electrons with opposite spin. The forward is indicates that plus of, the downward itself is what? Negative of. The spin number denotes the symbols. It has 2 values, plus of and minus of. This quantum number specifies the orientation of the spin axis of an electron. An electron can spin in only 2 directions, that is clockwise and anti-clockwise. Thus, each electron in an atom is described completely by a set of 4 quantum numbers. The first 3 describes its orbitals and the 4th describes its spins. These are all the concept of this spin quantum number. This is a very important question, generally asking in that 5 more questions. There are 4 quantum numbers are there. The principal quantum number, it explains the shape of the orbital. Azimuthal quantum number, it explains the shape of the orbital. The magnetic quantum number, it explains the possible orientation of an electron in an axis. The spin quantum number, it explains the what? Either it is a clockwise or anti-clockwise directions of that electrons. Next, shape of orbital. The orbital symbols are associated with the angular momentum quantum number, which is assigned an interior value from 0 to 3. The corresponds to S. 1 corresponds to 0 corresponds to S. 1 corresponds to 2. 2 corresponds to 3, etc. These orbital symbols are given to group of lines originally noted in the spectra of the alkali metals. These lines groups are called sharp, principal, diffuse and fundamental. Now we are going to discuss what is the shape of the S orbital. With the help of this azimuthal quantum number and magnetic quantum number, hence the S orbitals have unique orientations in space. Thus, S orbitals corresponds to spherical in shape with the atomic nucleus as at its center. For every value of n is one S orbital, that is, orbitals are present in all principal energy levels. Its radius depends on the value of n. As the value of n increases, the size of the S orbital is also increases. Thus, as no nodal plane, the shape of the S orbitals are shown in the figure. Not the shape of p orbital. The p orbitals, azimuthal quantum number is 1, magnetic quantum number is -1, 0, +1. And 3 orbitals have 3 orientation in space. Thus, p orbital corresponds to dumbbelled shape and with the atomic nucleus at its center. The p orbitals is having 2 lobes. Directed in opposite sides of the nucleus. The p orbitals oriented in 3 different directions along x-axis, y-axis and z-axis of the usual coordinate systems. These orbitals are designated as px, py and pz. Just we see the diagram of this p orbital. It is dumbbell shape. Next we will move on to the discussion on the concept of shape of the orbitals. The orbitals, azimuthal number is 2, the magnetic quantum number -2, -1, 0, +1, +2. Hence the orbitals have 5 orientation in space. Thus the orbital corresponds to a double dumbbelled shape with the atomic nucleus at its center and one dumbbelled with though not shaped. The orbitals has 2 nodal planes. The shape of the orbitals are shown in that figure. This is the shape of the YZ. This is xy, this is zx, d z square and d x square minus y square. These are all the different shapes of d orbital. Next, we will move on to the shapes of f orbital. The f orbital's azimuthal quantum number is 3 and magnetic quantum number minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Here, f orbitals have 7 orientation in space. F orbital has complex shape with atomic nucleus as its center and as 3 nodal planes. I think you learned the concept of shapes of orbital. The s orbital is in that spherical in shape. The p orbital is in that dumbbell shape. In d orbital is a double dumbbell shape and f orbital is a triple dumbbell shape. What is shielding or screening effect and effective nuclear charge? The quantum models suggested that electrons are surrounding around a nucleus in a circular orbit at different intervals of time or different distance. Since nucleus is positive charge, because that nucleus it consists of protons and neutrons. The proton is having positive charges. In that neutron, they do not have any charge. In that nucleus surrounding, the electrostatic force of attraction between electron and nucleus, they are stable. This attractive force on each electron in an atom is different size since electrons are circulating at different intervals of distance from the nucleus. Just we consider here, electron in the first shell experiences greater attraction than the electrons in that second shell, which in turn experiences greater attractions than the electrons in the third shells and so on. This is due to 2 reasons. As the distance between nucleus and the main energy levels increases, the force of attractions between nucleus and electron was less. Means the attractions on that electron decreases. The electrons present in the shells between nucleus and outer shell are called intervening electrons. The electrons in the outer shell are called repelled or shielded by electrons in the inner shell. This repulsion counteracts the attractions caused by the positive nuclear charge that is represented in that next figure. Because of the presence of intervening electrons, the force of attractions between that nucleus and the outermost electron is reduced. The reductions or decrease in the force of attraction because of presence of intervening electrons is called shielding effect or screening effect. The actual nuclear charge acting on the outermost electron is less than the nuclear charge, which is equal to the atomic number of atom. The symbol for effective nuclear charge is Z star. Thus, the effective nuclear charge can be calculated by using the equation Z effective is equal to Z minus sigma. What are the factors that affect that shielding constant and effective nuclear charge? Yes, so many factors are affecting the shielding constant and effective nuclear charge. Some of the factors or some of the relevant factors we are going to express here. The number of intervening electrons and size of the atom. These two are very important factors. The number of intervening electron increases. The value of shielding constant and the value of shielding constant increases, the effective nuclear charge decreases. That is reciprocal, not proportionality, here proportionality. As thus the number of intervening electrons increases, effective nuclear charge is decreases. As moving down the group in the periodic table, the number of intervening electron is increases. As the number of intervening electron increases, shielding effect, and hence effective nuclear charge is decreases. Thus, in any group, downward effective nuclear charge decreases. What is the size of the atom? It affects the shielding constant and effective nuclear charge. As the size of atom increases, the force of attraction by nucleus for outermost electrons or shell decreases. Thus, with increase in size, the effective nuclear charge decreases. As we move down the group in the periodic table, atomic size increases and hence effective nuclear charge decreases. As we move from left to right across the period, the size of atom decreases and hence effective nuclear charge increases. Thus, across the period as atomic number increases, effective nuclear charge is also increases. Next concept, Slater's rules. That Slater's rules is to study the shielding electron. Some empirical rules to calculate the shielding or screening of various electrons present in different orbitals of an atom or anion. Thus, the nuclear charge on an atom or ion is less than the actual nuclear charge and can easily calculated by using the following equation. Effective nuclear charge is equal to Z minus sigma, where sigma is equal to shielding constant. The effective nuclear change means, a charge means the net positive charge which affect the attractions of outer electron from the nucleus of polyelectronic atom. The term effective is used because those shielding electrons prevent the attraction of outer orbitals electrons of an atom. The Slater rules are applicable for the calculating values, shielding constant and effective nuclear charge on an electron in an atom or ion. The screening effect or shielding effect are constant, calculated with the help of that Slater's rule. Just we consider here 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 3d, 4f, 5s, 5p. The electrons in a group behind that electron under consideration contributes nothing to shielding or screening effect. For the electron in NS group, sigma is calculated by the following contributions of other electrons. For example, here 0.35 of each electron in the same group, 0.85 each electron in N-1 shell, 1.00 of each electron in an inner shell. For electron in Ng or NF group, sigma is calculated by the following contributions of other electrons. 0.35 of each electron in the same group, 1 of each electron in that lower group. For one of the two electrons present in 1s orbital of any action, the contributions of other electron is 0.3. This is the way to calculations of that screening effect and effective nuclear charge 4s. Consider manganese, copper, potassium. For manganese, atomic number 25 electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Calculating sigma by applying Slater's rule. First we have to take in for that. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p. Just we consider, accommodate the electrons here. That s orbital, p orbitals and d orbitals, we have to separate it here. We consider next copper. Copper is also first we have to write that. Electronic configuration next. Sigma by applying this Slater's rule. What is that effective? Here 3.73. Next we consider for that potassium atom electronic configuration. Here 1s, 2s, 3p, 4s1. We have to change that values of this. Here 10 into 10, here 18 electrons into 0.5, here 0.35 into 0. With the help of this Slater's formula, we have to calculate the effect. These are also chlorine atoms. We have to calculate Z effective by applying that Slater's rule. What we are getting is 6.1. That Cl minus 1, 5.75. Calculate that effective for the lost electrons of sodium and Na plus ion. The electronic configurations of the sodium is 1s2, 2s2, 2p6, 3s1. Here 2 electrons here, 8 electrons here, single electrons. Just we have to calculate. Find what we are getting, 2.20. The electron configurations of that sodium, first we have to write that. Sodium, Na plus means to remove one electron. Na plus means remove one electron. By applying that Slater's rule, we have to find out. Similarly for that copper, etc. What is the Pauli's exclusion principle? In that Pauli's exclusion principle, just we consider it is 1s orbital, here 2s orbital, here 2p orbital, 2py, 2pz, 2px. In any atomic orbital, we can accommodate only 2 electrons with opposite spin. That is called what? Pauli's exclusion principle. In an atom, no 2 electrons can have the same set of value, all the 4 quantum numbers. This means that no more than 2 electrons can occupy the same orbital, and that 2 electrons in the same orbital must have the opposite spins. Because an electron spin, it creates a magnetic field which can be oriented in one of 2 directions. For 2 electrons in the same orbital, the spin must be possessed to each other, or the spin are said to be what? Paired. These substances are not attracted to magnets, are said to be diamagnetic. And electrons are paired, that is called what? A paramagnet. In that orbital is having single electrons are there, that is paramagnetic. In that orbital is having paired electrons are there, that is called what? Diamagnetic. Now I am going to conclude that first unit. From this, atomic theory has evolved since an ancient times. The hypothesis of grid scalars has become the basis of analysis by scientists. They have done a lot of discoveries and theories regarding the atom. Moreover, it derives from Greek words like atoms, which means that indivisible. All matter is made up of tiny units called atoms. This was first proposed by Leucippus and Democritus in that 5th century, that all matter is made up of tiny units called atoms. The English chemist John Dalton subsequently made on the great notions of atoms in 1808. He postulated the matter is made up of atoms, which are small indivisible particles. He also proposed that while atoms of one atom element are identical, they are totally different from those that make up other elements. In 1904, English physicist Joseph J. Thomson proposes the plummeting theory, individual atom. He does so after discovering that electrons, by using that Rutherford experiment, in that Gold-Leaf experiment, we are going to express that the structure or designing of these atomic models. Later that to discovery days of this black body of radiation, photoelectric effect, line spectrum of hydrogen, etc. and discuss the concept of these quantum numbers are introduced to describe the trajectory and movement of an electron in an atom. The quantum numbers of all the electrons in a given atom, when combined, must completely meet the Schrödinger equation. The set of numbers used to describe the position and energy of the electron in an atom are called quantum numbers. There are 4 quantum numbers, namely the principal quantum number, it explains the shape. Azimuthal quantum number, it explains the shape. Principal is explains the size. Magnetic quantum number, possible orientation, and spin quantum number, electrons are accommodated. Here they mention some keywords: effective nuclear charge, shielding, Zeeman effect, principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number, orbital, Pauli's exclusion principle, etc. These are all some references for study. These are all these self-understood questions. Here they explain Dalton's theory, Flumfording model, Rutherford model of atomic model, discuss the failure of classical physics with respect to black body of radiation, heat capacity variation, photoelectric effect, and line spectrum of hydrogen atom, etc. These are all important questions they mentioned in that. Thank you.